having some connection issues on my side, so hopefully it doesn't go out during class, but it's possible.
Yeah. You've been having a good connection, correct? Is that right?
I don't have a good connection right now, is what I'm saying.
Yeah. But usually you do have a good connection,
Yeah,
right? Typically.
usually I do, yeah. Mm-hmm.
So it's a rare thing. And do you have MediaCom there, or how does it work? What is the service provider?
Charter?
What is Charter?
I guess it's just like a local.
Okay.
Well, I think it's more than local, but
Okay.
a lot of people have either Comcast.
Probably good. Yeah, then they will have more control on what they can do.
Yeah, but it's still pretty big, so I think.
Okay, I see.
Yeah.
Okay.
Just kind of depends. Most of the time it's always good, but.
Yeah. That's what at least it seemed like your connection is good.
Recently, though, I guess there was a car that hit a pole down the road, and we've had some like intermittent connection since then. So hopefully they're gonna send somebody out to check it out.
I see.
The pole looks fine, but
the connection has gone bad since then.
Yeah.
I see. Yeah. Yeah, those are the harder things to convince, right? Oh, the pole looks good, but our connection is bad.
Yeah, exactly.
Hopefully it works out well today. Yeah, let's see. Yeah, in fact, I have been pretty amazed at how much we could achieve with the internet, at least at the graduate level. Even the undergraduate course I'm teaching seems to be overall running fine, but I really don't know how much some of the students might be struggling. Like even if there is 10% of the student, let's say 3 in 100 students struggling, that's not good, right? Because of the connection problem.
Yeah, I think I'm surprised as well at how good it goes. Honestly, I don't even think that I'm online whenever you're teaching now. I guess I'm used to it from last semester till now. It seems.
Yeah.
I guess it's like normal.
Yeah. I hope it doesn't become a norm. It's fine.
I think the biggest benefit of being at the university is being able to ask questions there. So like if you had a question, having like-minded, students and professors around you where you can be face to face and ask questions. I think that's the biggest thing you lose online, because it's hard to just say like, hey, let's make another meeting at this time. And
I agree. I completely agree. And I think that is what university is about, right? I mean, it's not just about the classes. The hope is that when you're going on the corridor, you encounter someone and suddenly there is a resonance between what he or she was doing and what you were doing.
Yeah.
So that's a, and you miss out on all those things. But it's hard to capture these things and articulate in a few sentences. For example, in a news article that can be conveyed to the policymakers.
Yeah, I think it's hard to say what's the best decision, because
these days I do understand like there is a reason, but it's just the fear that how far they will take it. Like usually once.
Oh, just in the future. Yeah.
Like this gives.
I hope they don't get rid of in person, but I do understand the value of being at home right now, or not necessarily just being at home, but not being.
Sure.
Like, if you think about I assume that if college resumed as normal the cases would just completely skyrocket. You know, I think it would be bad
I agree.
because even as you know more students were on campus, the cases went up, and then once people saw the cases were up, less people were just being crazy. So hopefully people continue that trend to where we don't see the cases super skyrocket.
But I did check the numbers yesterday. I mean, this is really going nice, at least in our campus. We're lucky, I guess.
Yeah,
I hope this stays like this.
yeah,
It's
I do too. But again, it's one of those things where I talked to some of the people at the university, and I guess um, they say that the campus is, since the cases went up, to like almost 60 people. People, I guess, are being more cautious in terms of like being in groups, I guess. So hopefully they continue that trend, because we'll see. Because when October gets here and it starts really cooling down and people's immune systems are adjusting, I still think that they're going to see an increase, even if it stays like this. Would be my guess.
Agreed. Yeah.
Cold and flu season are just around the corner.
Yeah, it's so unpredictable. So yeah, surely I think everyone has that.
Like
All
at my wife's school, where it's my wife's school, where it's they're in person, they're all wearing masks and everything, but there's still 30 kids in a classroom. I mean, like half the school is quarantined right now.
Yeah, you told me that. Like those are the hard ones actually. Like there is I also heard about a university that the whole university is quarantined.
Yeah, if you go back to business as usual and you require all the students to be in classrooms, it's just going to go wild. It's a really contagious virus that affects some people and doesn't affect others, and it makes it even more contagious because sometimes you get it and you don't even know you have it, and you just during the time that you actually have it, you're just a carrier that spreads it. You feel fine. You never felt like you ever even had a symptom, yet you still get those high risk people sick. If you're like an overweight person or you have diabetes or something along those lines, and if you get it, it's pretty big deal.
Yeah. Understandable. Yeah, I don't understand it at all. Only a couple of times I had to take decisions based on that was in the summer when I had to decide when I had only 3 students and 2 of them were from Carbondale and they said, oh, we would like to meet in a big classroom. And that was a decision that turned out to be hard for me because I was not sure whether, because then the responsibility comes on you. So I was lucky that the class volume requirements or the class surface area requirements forced me not to do it. And that's the same kind of decisions I struggled with this semester also. I don't know what to do, honestly.
Well, I think everyone wants to be there and everyone wants to be in the class, but at the same time, you just like, even though I have to drive, I would rather drive every day and be at the university than stay at home. But it's
Yeah. There's another decision coming soon. I have to decide whether I have to take the test in class or not. Let's see.
yeah.
I struggle with some. Yeah. So I'll see. I try to give it to the students as far as classroom goes, but the test comes on me. So let's see. I'll do something.
Yeah. All right.
Okay. So we are only 3 of us today. We're losing. Oh yeah, Alia did say that she will be. She was not well. Oh, okay. And who else is there? Alia. So four of us, and then five.
Moses and Rob.
Oh, Moses. Yeah, Moses is missing, right? Okay. Yeah. And Rob actually is not there in this class. Yeah. Only Mike.
Oh, okay, okay.
Okay. So let's do something. I did post a homework in the morning. Homework 5. Made it due October 1. That's next Thursday. And there is midterm 1. Sorry, midterm 2. 2 weeks from today. And by default, we just discuss this. By default, this is in PHYS. But I might change things. Yeah, we were working with analytic functions. Out of all complex functions that you can define on a complex plane, there are a special class of functions which have a isotropic derivative at every point. Right? So that's so these are, I think, they have isotropic derivative at every point. And I think it's a good thing to say that even today, which is not surprising at all, we cannot capture everything in equations still. So that should be, maybe I can clarify that in 2 steps. There are certain things that we don't understand at all. Right? That's one thing which we don't even consider this in this discussion. But there are certain things that we do understand a lot, but they cannot be captured in a compact equation. Typically, these are geometrical concepts. You know that geometrically this should not happen or that should not happen, but you cannot capture that in equation. And I would say analytic function, to a certain extent, it is that. And in what sense? It's in the following sense. So if you were to ask someone what is an analytic function, you would say that yes, isotropic derivative is, so that's a concept, so that's a geometric concept, right? You take a derivative at around every point and make sure that it is independent of which direction it comes in. So that's a geometric definition. But now if you want to capture that in algebraic form, you would say that's contained in Cauchy-Riemann conditions, but it doesn't completely capture it. So Cauchy-Riemann conditions. And we said that what are called Cauchy-Riemann conditions? If you have a general analytic function, let's say, or general complex function, which can be written in terms of 2 variables, u of x, y, plus I times v of x, y. So you have a plane, this is the real part of a complex number z, and y is the imaginary part of the complex number z. And the function is also having a real part and an imaginary part. U is real, v is real. And we said that the Cauchy-Riemann conditions say that du by dx is equal to dv by dy, and you have du by dy is equal to minus dv by dx. But that's a necessary condition, but that's not a sufficient condition. So you surely know that if it does not satisfy this, then you immediately say that, oh, this is not an analytic function. But if it satisfies, that's not completely true. So let's do an example, small example that to illustrate that. So for example, yes, I wanted to write this, that is a necessary but not sufficient condition. And in that sense, that is what I meant by saying that this cannot be captured. So the idea of an analytic function cannot be completely captured in an algebraic equation. We need that geometric concept of an isotropic derivative. And so what I suggest is, so to emphasize this point, let's say you have how do I say? So first, let's do a simpler example. So let's take the example. So this is an example of not an. Or maybe I could ask you guys, give an example of an analytic function. Give an example of an analytic function.
Z squared.
Z squared, good, right? So z squared, z squared, z cube, anything that doesn't have a z star in it is an analytic function. So f is equal to z squared, exponential of z, sine of z, any algebraic form of that works. And in particular, let's a very nice example is, which is also plays an important role in this whole theory, is log of z. So I don't tell you that is this an analytic function or not, and if I don't tell you, then you want to figure it out, right? So let's do this. So we want to write this in terms of u and v first of all, right? So that's not very clear how we do that, because this is log of x plus iy, right? And this is natural of x plus iy. But it's necessary that you split it into u and v if you want to use the Cauchy-Riemann conditions, unless we actually try to write it in polar coordinates. Also remember that if you have z is equal to x plus iy, as another representation of a complex number, and that's the magnitude of the complex number times its argument. That's I theta, and that is nice in the sense then it gives you that it has this geometric insight, but then it comes with the caveat that theta is not unique, right? It has it has branches if you want. You can add a 2 pi to it and it's still good. So in that sense, this is also equal to log of r times e raised to I theta. But this form actually helps in separating it into u and v. So there's many ways of going about it. You can rewrite the Cauchy-Riemann conditions in terms of r and theta, like in the polar coordinates. But instead, let's keep the Cauchy-Riemann conditions here, at least in the class. That's what we can do. And let's try to verify whether it works or not. So expand this out. So that's log of r plus log of e raised to I theta. R is plus I times theta. But immediately we should also realize that Here I could have always substituted, there is a 1 here, so this is e raised to I m pi, right, where m is m2 pi. Where m is equal to 0 or plus or minus 1 or plus or minus 2 and so on. And that is also valid. In that sense, I can always add a plus I m2 pi. So that is that ambiguity in there. But for the time being, let's not worry about that. We will see that anyway coming in here. So let's say theta is less than 2 pi and greater than or equal to 0. So in that sense, I'm taking only the principal part of that. So often you say that's the principal part often. Okay, so that's good. But we know how to write this in terms of u and v by simply replacing this as x squared plus y squared. That's your r. And theta, we know in cylindrical coordinates, this is tan inverse of y over x. So the diagram you have in mind is your standard. This is r, that's your y, that's your x, and that's your angle theta. Right? Tangent theta is y over x, so theta is tan inverse of y over x. So immediately we want to check if this is analytic or not. So this is log of x squared plus y squared. In fact, I can write this as 1 by 2 times x squared plus y squared. And v is equal to tan inverse of y over x. To du by dx, that is 1 by 2 times derivative of log is 1 over the argument. So that's 1 over the argument, x squared plus y squared. And then take the derivative of the argument, which is 2 times x, which is x over x squared plus y squared. X over x squared plus y squared. Same thing with y. It's symmetric in x and y, so it is just replace or swap x and y. So that's an easy thing. Do the same thing with v. Right. What's the derivative of tangent inverse? What I do is I switch it to tangent v because I don't remember. What is the tangent v is equal to y over x. And then pretend you're doing a partial derivative here. So this is dv will be secant square of v dv over dx would be equal to minus y over x squared. And secant square of v is cosine square v in the denominator. So that goes upstairs, so dv by dx is equal to minus y sine square v over x squared. But v is actually the same as theta here, right? So cosine square of v is x squared over r. So it's minus y over r. That's minus, what is y over r? Oh, we want to write it in terms of x and y. So it is minus y over x squared plus y squared. Something is wrong? Or square. There r squared here, right? Cosine square v is x squared over r, and y has a 1 over r, so this is no square root. That makes this look analytic. So this is minus y over square plus y squared. Oh, sorry, this is b. Sorry. B is tan inverse of dv by dx is minus y over x squared plus y squared. And it turns out that dv by dy actually is exactly equal to du by dx.
Why is it minus again?
Minus here.
I thought tangent inverse was not minus. I thought that was cotangent.
Because when I'm taking the derivative with x, there's a minus y over x squared, right? Isn't that?
Okay, yeah, I got you. Because you're doing x and y. Okay.
Right. So I'm just doing it a blunt way. There might be better tricks to do that. Yeah. At least when I was a high school student, this seems to be there. But these days, I just use this method. When it is with respect to y, so it is 1 over x times cosine square theta. And then again, you do, yeah, then there is no negative sign there, right? So overall it goes through. Let me just do that instead of blindly forcing you guys into that. Yeah, so this is secant square y dv by dy now. That's equal to 1 over x. Then dv by dy is equal to cosine square v, cosine square v over x, and cosine square v is x squared over r squared. And 1 over x. So that's x over r squared, which is x over x squared plus y squared. Okay. So one would ask the question again, that is this analytic function of, is this an analytic function? It seems like it satisfies the Cauchy-Riemann conditions, but I said that these are necessary conditions, but not always sufficient. And this is where I say it cannot be captured completely in terms of an equation. So let's see an example, right? Remember, your isotropic derivative is the key, right? And if you were to think of this xy plane, so this is the complex z plane, so this is x and that's v. And I said theta is going from 0 to 2 pi, so that's my angle theta. And let's consider a point on the real axis, on the positive real axis. So I have made some dashes there, so on that line. And let's consider a point right here. So let's approach this line from the top. So that's a way of reaching that point, so that we are looking at the idea of isotropic derivative, right? And let's consider the same point approaching from the other point. Right?
But in this case, you'd never really get to it from the bottom side because it's from 0 to
2
less
pi.
than 2 pi.
Yeah.
But if you included all revolutions, then it would be an isotropic derivative, or it would satisfy Cauchy-Riemann, and then would be.
Yeah.
So if you considered all angles of theta, would it then satisfy not only the Cauchy-Riemann but then be an analytic function?
Yeah. So the main point is that this function, okay, this function actually, it's very special in the sense that it is not continuous for sure, right? So if I approach it from the top, I'm having theta equal to 0. At this point, theta is equal to 0, and at this point, theta is equal to 2 pi. Right? So in this way of looking at it, surely your V is different. Right? It's entirely different. But remember, that's not our, so this is sufficient to say that our function is not continuous along that line. So there's a discontinuity along that line, right? Which brings in the idea of a derivative. And how does a derivative work there? So that's our bigger concern, correct? Is that clear what I mean?
Yeah, sort of.
So
I get what you're saying. I just don't understand why it wouldn't be analytic still.
For example, I have a function of this kind, correct? This is not continuous.
Mm-hmm.
But its derivative, at least in the limiting sense, is continuous.
Yeah, because now you have a curve. Yeah.
Okay. Mm-hmm. So it is possible that you could have a function that is discontinuous and still have its derivative, at least in the limiting sense, to be continuous along that line. And those kind of functions will be called having branch cuts. So this will be having a branch cut here, which we'll encounter later. But that doesn't excuse you with this point. Right? So we still have to worry about the point z equal to 0, and that will turn out to be really not analytic. Okay? So that point will come out to be special. So what I mean to say here in all this is that even if you have something that is satisfying the Cauchy-Riemann conditions, that doesn't give you everything, right? So you still have to have a visual feel for it and do your analysis at each point. Okay? And this is one example I showed you that this is one of the important examples. But just to give you this Cauchy-Riemann or just that it is not equal at all in the derivative sense. Let's take another example, but before that, actually before that, because then I don't have to give you the V, right? It seems like, yeah, so this is a digression, so a small digression. Right? I'll come back to this point. I want to make one more point. But so let me before that say that if you have a function f is equal to u plus iv, it is understood that these are having x and y dependence. And let's say I tell you that given f is analytic. Okay. And let us say also given u. But the question is have I described the problem completely? Or is there a feature in V that is independent of U? So let's go back to our example. So I'll demonstrate this with an example instead of a proof. And that is, let's take our old example and say that U is equal to log of R, right, which is 1 by 2 log of x squared plus y squared. And the question is to find V. So can you even find V? And the claim here is the statement I'm making is, or I'm trying to convey is that if you provide U, then V is determined. And using the Cauchy-Riemann conditions, which is not hard to see because now we know du by dx, we just did that. So that's du by dx was x over x squared plus y squared. But
That's
that's
only if you're told previously that it's analytic, right?
yeah, it's analytic. Yeah. So I'm telling you, given the function is analytic, and I also give you u. So this is a specific example. And can we find v? Right? And the claim is that up to a constant, you can always find it, or not even constant, as a family of surfaces. And we will see that more explicitly soon. Okay. Did I answer your question?
Yeah.
So du by dx is equal to dv by dx. Right? That's one equation I have immediately, dv by dy, actually. Right? And I also have the condition that y over x squared plus y squared, the negative sign, is equal to dv by dx. So that's a differential equation for v. And it makes sense that, oh yeah, if you have a differential equation for v, we can solve for x and y. And let's explicitly do this. Example, in general, the claim is that we can always find v. So how do we find, how do you solve partial differential equation? Like partial differential equations are slightly trickier than standard differential equations. In the sense, you have to solve for one with respect to the, it's a small change. It's pretty much the same idea. So let's do it in a very naive way. So let's start with dv by dx, right? If I were to integrate the second equation, I know that v, so this equation tells me that if I have to integrate with respect to x, so this is equal to integral of dx and minus y over x squared plus y squared. And I'll do a indefinite integral. But after I do the integral, I should keep the fact that there is a constant that I can miss, right? If I'm doing an indefinite integral, and that could be off by a y. This is not just a constant, it could be a constant function of y, right? Because I integrated with x. And this can be integrated. So this is equal to, so this is
tangent or something?
right? Yeah, so yeah, and we do this so dx over, just to explicitly do this. So I substitute x is equal to y tangent theta, I suppose, right? So this is dx is y secant square theta, d theta, and this is indefinite integral. So this is y square, 1 plus tangent square theta, again secant square theta. So that's 1 over y times theta. But theta was tangent inverse of x over y. 1 over y tangent inverse of x over y. Notice this is x over y, not y over x, right? So it's not either. So it is 1 over y times tangent inverse of x over y plus an arbitrary function or some unknown function, a constant function with respect to y will also satisfy it, because when I'm taking a partial derivative with x, this will go away. Do the same thing with this other equation, right? That also gives me a v now, right? So this time I integrate with respect to y. So this is y, and this is, oh, there is a minus here, right? So this is a minus, sorry. There's a minus sign there. So it's dy, and this is x over x squared plus y squared. Plus this time another constant, which is a constant of constant with respect to x. This is pretty much the same integral as this. I just have to swap x and y, right? And forget the negative sign. So this is 1 over x tan inverse of.
I have a question really quick.
Yeah.
In the integral, you have a constant of c1y, and then after the integral, it's still c1y. Shouldn't it be a different constant? Because if you integrated that.
No. This integral is for this, right?
Okay.
right? I integrate and that integral is off by a constant, correct?
Okay.
Isn't that what we do?
Yeah, I just, for some reason, I thought you were integrating also.
Yeah,
Okay.
it closes the brackets. It's the same thing here. Right, so that's, but then what is V, right? So we have two solutions for V. So I said, all right, so V of x, y could be minus 1 over y tan inverse of x over y plus a function c1 of y. But in this case, it's useful to have an identity because one is with respect to y over x, one is with x over y. So there is an identity for tangent inverse. And that is that tangent inverse of theta plus tangent inverse of 1 over theta is equal to pi by 2, I suppose. Is there a way to motivate that?
Yeah, can't you just, well, how do I, if you change it to E,
E. Yeah. Yeah.
then your theta and 1 over theta would be,
You're suggesting probably that, let's say tangent, so this is x, let's say some quantity x is tan inverse of theta, right?
yep.
So that is theta is tangent x, right?
Then you can,
Other one is tangent, so 1 over theta. So y is an inverse of 1 over theta. Tangent y is 1 over theta. But tan of y is cotangent of x, I guess, right? So 1 over theta is 1 over tangent of x, right?
yeah, 1 over tangent of x, yeah.
And how do you do this after that? So I can go back in here and use this y is equal to tangent inverse of cotangent of x. So I want to write cotangent in terms of tangent, I suppose. Right? So So y was tangent inverse theta, so that's good. So tangent inverse theta plus y is tangent inverse of theta. So that's tangent inverse of
So
you guys. I don't want to do this now. I'm not motivated. Yeah, I don't see that. I mean, any immediate hints? How about this? Prove this extra credit. Is that good enough? Is that okay for me to?
yeah, I was just thinking like set
Immediately? Yeah.
set like theta equal to x, and then set 1 over theta equal to y, and then you can do tan inverse of x is equal to something, and then tan inverse of y is equal to something. It tells you the tangent of let's say that something was a and b, so tangent of a is equal to x, and then tangent of b would equal to y. Then you'd have tangent of a plus b, right?
So tell me again. Yeah. So this is what it is. Yeah.
Yeah, like that.
And then?
And then, oh, did you write tangent? Yeah, yeah, like that. And then you have tangent of A plus B is equal to tangent of A plus tangent of B divided by 1 minus tangent of A, tangent of B.
Yeah. Reasonable.
So then you'd have x plus y over 1 minus x plus y, or 1 minus xy.
Oh, you want if B is equal to B is equal to 1 over theta, you want to say, right? Is that what you want to say?
And so tangent of A, so if you just write it in terms of now x and y, it becomes more relevant because we could say that x is equal to theta and y is equal to 1 over theta.
Yep.
So then you'd have A plus B is equal to the tangent inverse of x plus y over 1 minus xy.
Yeah.
And that tells you that if you plug in your numbers, then theta and am I thinking about this?
So you're suggesting that x is theta here, right?
Mm-hmm.
So x is theta and y is 1 over, right?
Yeah. So you'd have 1 plus 1 over theta and then 1 plus theta times 1 over theta, which is 1 plus 1, which is 2. And then the top would be theta, which you said is, so we end up with theta over 2.
Yeah, I'm not seeing it still. Am I missing something? Okay, you guys finish this, okay? Yeah, that's that's bad. I should be able to see this, right? Yeah, that's the way to do it, I think. Yeah, that's rings a bell. What's a trick here? Okay, again, there's a trick here. Okay. X is theta, so A is tan inverse of A plus B, A plus B should be pi by 2, right?
So you end up with a theta plus 1 over theta.
So theta squared plus 1.
For some reason, it seems like you're getting the tangent inverse of 1, which is pi over 4, not pi by 2. But
Where am I getting tangent inverse of that?
Be-
Theta plus theta,
because
1.
because you end up with, oh wait. You
Okay.
end up with,
Okay, let me not proceed. I'm not going anywhere with that. Yeah, sorry. So, okay, extra credit part. Okay, important extra credit. I'll look into it. I want to check my foot. Yeah, that's bad. I agree with that. Okay. But, okay, so the point is if I use that, I can say that this is equal to minus 1 over y. Correct. Times pi by 2 minus minus of tangent inverse of y over x, which did I write the identity right? Maybe that's the challenge. Yeah, the identity of phi. Oh, it's a minus pi by 2. Okay, what am I saying? Okay, my point here is that this is minus, so it's plus 1 over y, tangent inverse of x over y, or sorry, y over x now, y over x plus a new constant, right? This is y can be absorbed into that c1 as a function of y. And there is another solution we found, v. Can we check this integral, actually? Maybe I did the integral wrong. Did anyone follow the integral? Did I get my integral correct?
Let's see.
Keep messing up all the time. Okay, here, minus 5, right? du by dx is if you don't mind, I'll do this again, the integral. I think there's something missing there. Sorry. So, dv by dx is equal to dv by dx is minus y over x squared plus y squared. Yeah, and v would be equal to minus y integral dx over 1 over x squared plus y squared. I substitute x as y tangent theta, dx is equal to y secant square theta, dy, right? So that's equal to minus, I put the y inside, so this is y squared secant square theta, divided by x squared plus y squared is y squared secant square theta. So secant square theta cancels out, y squared also cancels out, and that's equal to minus theta, where theta is tangent inverse of x over y. So I think I missed one of these y's earlier. That was the point. So there is no y here. And the same thing there, there's one. Which makes sense because our v was tangent inverse of x over y or y over x, correct? So we should be careful with that. Okay. Sorry for that. And this is a minus, and one of them has a minus. This one has a minus, and this one does not have a minus. But then I was struggling with, oh, this is x over y, y over x. Which one is correct? But then they are off by only a constant. Correct? So let me write this again. So what I was trying to point out is tangent inverse of 1 tells you that this is x over y plus c1 over y. And the second solution, second way of doing it, tells you that this is tangent inverse of y over x plus another constant with respect to x. So then you say, oh, which one is the solution among this? And then you recognize that there is a connection between the two. I can write tan inverse of theta plus tan inverse of 1 over theta is equal to pi over 2. If I use that identity, I can connect the first one, or I can write the first one as tan inverse of y over x. So this is minus, right? So it is minus pi by 2 plus C1y. And then you can always absorb this into C1y and say that's a new definition of C1. Okay, better. Okay, so that was a digression just to show that U and V are connected all the time, and you can actually capture V from U itself. So using that, I wanted to demonstrate that how in one of the examples, you can see that the derivative is not there. Log function is a special function, but let's take an arbitrary another function. There are many of them, but one of the example is the following. So, and I recommend to draw this also, or plot this actually. So this is an example. Again, what was I doing in the previous example? I was showing that given U, V is known immediately. So similarly, I say there is an analytic function, f is equal to U plus IV, right? This is analytic. Oh, I don't tell you analytic or not. I should tell you that this satisfies Cauchy-Riemann conditions. If it satisfies Cauchy-Riemann conditions, then I can find, if I'm given U, I can find V, right? So let me say U is equal to x cubed minus y cubed divided by x squared plus y squared. And V given by Cauchy-Riemann conditions, we'll say. Like whatever we did earlier, if I can use that to solve for U. But now let me show you that how this thing doesn't work. So let me do du by dx. So if I want to calculate the derivative of f, I need to do du by dx, and that is do the algebra, right? So it is 3x squared over x squared plus y squared, and there's one more term which is x cubed minus y cubed multiplied by 2x divided by x squared plus y squared whole square. And that's equal to, so that is 3x squared over times x squared plus y squared minus of, this is 2x raised to 4 minus 2xy cubed divided by x squared plus y squared whole square. Let me rewrite that. So there's a 3x4 minus 2x4, so that's x raised to 4. Then there is 3x squared y squared. And then there is plus 2xy cubed. But now let's do the following. I first take the limit y tends to 0. Maybe I should do this more explicitly upstairs. So let me do limit x tends to 0. So first times, let me come on the x-axis first. So first I set y tends to 0 of du by dx. So that's equal to, so if I were to set y tends to 0 everywhere in the numerator except the first term that goes to 0, and in the denominator it is x raised to 4. So this is x raised to 4 divided by x raised to 4. That's equal to 1. So if I were to do limit y tends to 0, and then I take the limit x tends to 0. I'm reaching the origin. The way to look at this is that first I go here, and then So I start from here, reach there, and reach here. Right. To reach the origin, first I go y tends to 0 for a fixed x, and then reach the origin. So think of isotropic derivative, right? Coming along the x-axis basically. And du by dx is equal to 1. Do the same thing in the opposite order. Limit x tends to 0 of du by dx. So if I take the x tends to 0, everywhere in the numerator, it's immediately going to 0. So it is actually 0 over y raised to 4, which is 0. And then if I take the limit y tends to 0, is equal to 0, which is not the same. That means to say that if I were to actually start from this line here and then come there, that's different. So whether I approach it from here or there, that comes out to be different. This is nice function in the sense I'll encourage you guys to do. You guys use what is the software you guys use to plot a function?
I use Desmos.
What is it called? Decimals?
DESMOS. It's really nice.
Okay. Does it allow 3D plots, like two variable plots?
Yeah, I think so.
Okay. So this is an extra credit, and this is a nice function. So extra credit. So this is extra credit. Plot u is equal to x cubed minus y cubed over x squared plus y squared. Like draw a three-dimensional plot in the sense x and y. So it will give you a surface, right? And you will see that there are waves in there. And try to understand what this means by this is not analytic, right? And then plot du by dx. So this is the first plot you want to do. And the second is plot du by dx. And you'll see that it has a lot of kinks. It doesn't like, it gets bent or what is it? It gets folded. Like the idea is that if you have a paper, can you convert a paper into a spherical ball? Usually you cannot, right? Without getting folds and kinks in there, you cannot get it into that. So that's the idea. So plot du by dx also, we already found that, right? Du by dx is whatever that function is. And just try to get what are the features in there. And ask plot these functions with the thought that in what sense is this not analytic at various points? You have to ask, is it analytic at x equal to 0? Or is it analytic at the origin? Is it analytic on the x-axis? So analyze analyticity. Just think about the continuity in these continuities, in these plots. Like how does this behave? So that's a feature you want to capture. That's what I was trying to convey by not everything can be grasped algebraically. So you have to leave something for the geometry in there. Okay, so there's one more thing I wanted to say that there is, yeah. and this is called conformal transformations. Conformal transformation is, or let me begin by saying, if you have two vectors given to you, A and B, right? And I ask you, I make a rotation transformation, so I rotate my, so this is usually given in terms of an axis, right? If I were to rotate my axis, what is invariant, what remains the same? What quantity constructed out of A and B remains the same under rotations?
The angle between them?
Angle between them remains the same, that's good. So this is angle theta, right? And so theta remains invariant, same under rotations, right? Under rotations. And A dotted with B, right? That also remains the same. That's a scalar quantity. It's not directional. So any scalar you can build also remains same. Also remains stays same. Okay. So that's under rotations. Now you say that under any transformation, if this happens, that is not just under rotations that this happens. Under any transformations, if locally this is true, then you say that these are conformal. And now I'm slightly confused as to whether A dot B is required or not. This is surely there in conformal, but this might be an overstretch, maybe. No, it's just angles. Yeah, I think it's just angles. Yeah. So theta remains the same under rotations, as Moses pointed out. So let's look for any other transformation that keeps the angle between the quantities the same, but rest everything stays. We don't care for the others. And the classic example typically is, for example, you have a coordinates. So I can stretch this, right? So I can. Oops. I basically incline this all the way, and but I did keep this angle same, right? No, I want to stretch it. So how do I do this? So I'll stretch it. So maybe I think I want to do this like this. So this is okay, but one side I can stretch. So this, so yeah, I can rotate. For example, this can go like this, and I can stretch on one side. That's perfectly fine, but these angles should stay the same. That's all you require. So think of transformations where you can rotate around, do anything, but the angle between every surface element that you draw should be the same. So the angle is the same. And every angle for that matter. Already I'm not able to draw properly. This one, yeah, this one is, so suppose this is 1, that's 1, that's 2, that's 2, and so on. But then let's try to imagine how can you do this. So let's go to complex analytic function, right? So what are we doing in analytic function? We are actually trying to plot, there's a function connecting a quantity in xy to u of xy, right? So that is, let me write this way. So there is a complex function x plus iy which is a plane, and there is another function u plus iv. So x comma y is one plane, and u comma v is another plane. Right, so for every point in one plane, I can have a map to another point in the in another plane. So, for example, this is your z plane, and that's your f plane. So this point could go somewhere here, and the close point here could. So this could be 1. That's your 1. 2 could be going. So this is 2 somewhere else. 2. But now let's ask, if I'm told that this is analytic, I want to show that this is actually conformal transformation. So let's consider two close by elements, right? So this is one point, so that's dz. So let's say, so I want to build this up using 3 points. So this is dz1 and this is dz2. It requires 3 points, but then one of the points I can choose to be at the origin or talk in terms of differences in quantities. So this is a complex number. That's also a complex number. What I'm talking about here is that there is a one point here, dx, and there is another point. So go from one point close by to the another point, and start from the same point and go to another point close by. And you want to see how does that happen here? Like the same transformation, how does that happen in there? So this diagram is dz1 and dz2, and in this case, when it transforms, this could be df1 and this could be df2. You don't know how it transforms, right? Some complicated transform, but whatever it is, this point gets connected with df1. So what is dz1 times dz2 as a complex number? And in fact, let me multiply star, right? Let me investigate the quantity dz1 star times dz2. This is a complex number. That's also a complex number. I take the star of 1 and multiply that with the other. Since it's a complex number, I can write it in terms of polar coordinates. So that is dr1 times exponential of I theta 1. Right, that's the representation for the first one, and then I have to take the complex conjugate. And the second one, I do dr2 times e raised to I theta 2. Right, in the complex. Okay. So this is nothing but dr1 is real now, dr2 is real, so it's dr1 dr2 times exponential of I theta 2 minus theta 1. And this is the angle between the two vectors, right? So this is theta 2 minus theta 1. So we are trying to look for another quantity there which is independent of theta 2 minus 1. The idea we want to show is that df, let's ask, what is df1 star times df2? Just the angle part of it. If it's the same, then you know that that's conformal. And how do I go about it? And I want to go about it as So this is analytic, right? So df1, so since it's an analytic function, since it's analytic function, df by dz is the same as is equal to du by dz plus I times dv by dz. Oh, actually, I better, right? Yeah, I think it's isn't it? I keep forgetting the proof. Yeah, so this is equal to, yeah, since this is an analytic function, I can say df is the same as, remember that df would be equal to df by dz times dz plus ef over dz star times dz star, right? That's what in general it is, but if it's an analytic function, this is not there. If it is analytic, this is purely in the df by dz plane. So that's equal to partial derivative of f with respect to of f1 with respect to z of dz1. Right? I'm evaluating at point z, right, of dz1 and partial derivative of f. Like I think this is not f1, right? So I should be careful. So this is the derivative of f in that direction, I should say. So yeah, so this remains the same. Is that clear? So this is the line element constructed out of the derivative. So this is this quantity here. So what I mean here is that df1 is the derivative due to the small displacement in dz1, and df2 is the same thing because of small displacement dz2. In which directions are we going? Right, the small change that we are constructing. But the point is, because it's analytic, it's isotropic, this is the same. Right, these two are the same because it's an isotropic derivative. And once you accept that, so this is now dz star again, and this is df by dz. Once we accept that, this is the magnitude then, df by dz magnitude square times dz by d1, dz1 times dz2. That means to say that the area element that I built on the new plane is exactly equal to the area element of the first one, but its magnitude could have changed in the sense that this is df by dz squared dr1, so this is star, dr1, dr2 times e raised to I theta1, theta2 minus theta1. So the angle is still the same. This is magnitude, positive quantity. So this is the magnitude, so the angle remains exactly the same. I use the fact in here that each df1 and df2 can be expanded around that point, and its derivative has to be the same. That's the feature of analytic a function. So the moment you say it is analytic, it is isotropic, and once it is isotropic, it gives them the feature that the angle that you build from one plane to the transformed plane, that remains the same. That means analytic function by construction is conformal. Like the analytic function, the transformations that's involved in the analytic function are conformal by construction. And I'll stop here. Yeah, extra credit, right? Try to draw a conformal mapping. So extra credit. I think that will help you guys visualize this. There's a lot of visualization in here. Illustrate conformal nature of analyticity in the example in f is equal to exponential of z. Like that's a transformation, and start from one plane and go to the other plane and show that it is actually conformal. Okay, I think that finishes all the concepts needed for the analytic function, and in the next class I will do what are conjugate functions and then do the Cauchy integral as applications of that. So 4 lectures more maybe, and then it depends on how far I want to go into the integrals, whether to do branch cuts or not. That's a different point that we will see as we go. Any general comments or thoughts? Okay, that's all. Thank you, guys.
So
Yes.
can I share my screen really quick and see if this is what you want for the function on the graph? Like if this is what it's supposed to look like?
Oh, yeah. So you try to plot it. Okay,
Let me
sure.
see if I can.
Are you sharing? We are not seeing anything.
Yeah, I think it takes a second.
Sure. Yes, we can.
Okay.
No. 3D plot.
Oh, okay.
3D plot. That is, yes, those are the kinks that's coming up, but you want to see 3D plot. That comes out very visual in that.
Okay.
This is manipulate, do 3D plot. You know what I mean? The surface plots?
Yeah, I think I can do it. I'm not sure how to do it at the moment in here.
Yeah. So it must be there in that feature. Usually most of the features are involved. Otherwise, Mathematica is a good thing. Like try to do Wolfram Alpha and just type plot 3D.
Okay.
And if you want, I can. Yeah, you can try now. Yeah.
Okay. I think I get the idea. I'll try to 3D plot it. I don't know off the top of my head, but that's the right idea, right?
Yes, yeah. But plot 3D. Okay, it's a surface.
Okay.
You have to get this feature of the surface because I wanted to show the kinks, right? When you have an analytic function, like think of a paper being folded into a sphere. You cannot fold it, right?
Mm-hmm.
You get this twist, and you will have to what is it called? A crease. You cannot avoid a crease, and that feature somehow geometrically is contained in this analyticity. And that I want to pass on to you guys. And you get it only by playing around, since there is no algebraic equation stating it explicitly.
Isn't there a way? Didn't we talk about that in a little bit? How you can take like a sphere, turn it inside out or something? Without
That's
making it
correct. Yeah. Are you guys aware of that inside out sphere? I think Moses and Jordan know. Michael and uh, Luke,
No,
have you heard of uh, turning a sphere inside out? It's a very popular.
I don't think so.
Okay, so then it's an extra credit only for those who have not taken a course with me, but just do it. Watch the video. Turning the sphere, inversion of a sphere, that's what it's called. It's a very nice video. It's an inversion of a sphere. It's a video prepared, I think, some 40 years back in, I think, Wisconsin, probably. A very nice video that conveys this geometrical ideas very clearly. It has nothing to do with analytic, but it is in the sense that those are the same ideas involved. very, very hand-wavingly, that's similar ideas. I think that's what probably you guys remember, right? Yeah, that's exactly what I'm trying to convey. Yeah. And it's hard to capture them in equations, those ideas. Okay, so that's another extra. So lots of extra credits this time. But they're just for attempts. I see that you guys are, many of you guys are spending time on that. It's supposed to just to make you guys curious, but at the same time, each of that can be a big exercise in itself, can take you far. Okay, that's all. Yeah. I think next next concept is more algebraic, so that should be easier. These are little geometric, so it gets a little hard to convey.
Okay, thank you.
thank you.
Take care.
Thank you.
Enjoy.
Bye-bye. I'm glad my internet lasted.
Bye.